Hi my dear brilliant subscribers, welcome to my channel. This is continuation of Glasstone and Sesonske book, chapter number 2. The topic is attenuation of gamma rays. When gamma rays are passing through a medium, how the intensity of gamma ray changes when it come out of the medium. So what happens when gamma ray passing through a medium? Already in the previous class I explained the interactions of gamma rays with the medium. They are photoelectric effect, Compton effect and pair production. Same thing happen. Because of that, these gamma rays are absorbed in the medium. So this absorption of gamma ray depends on what factors? That we will discuss now. Suppose intensity of gamma ray I is intensity. Suppose some quantity of intensity I am calling Di, small quantity Di. So this Di, the intensity of gamma ray absorbed in the medium. It depends on what factors? It depends on how much distance it traversed in the medium, and it also depends on what is the initial intensity of gamma ray. So higher the intensity, higher the interaction will be there. At the same time, it is traveling more distance, more interaction will be there. So the amount of intensity of gamma ray absorbed in the medium is proportional to original intensity and distance traversed by the gamma ray in the medium. Apart from these two, one more important thing is it is traveling through which medium. That is also most important factor, because different medium will have different atomic number. Different atomic number will undergo these interactions differently. You know that the probability of photoelectric effect is proportional to Z to the power of n divided by E cube. Z is atomic number, E is energy of gamma ray, and probability of Compton effect is proportional to Z divided by E. It means this interaction depends on Z, atomic number, so it is different for different material. And pair production, it is proportional to Z square into in the bracket E minus 1.02. That already I discussed. So this interaction completely depending on what material we are using, because atomic numbers are different for different material. So this attenuation happening in a particular medium, so this attenuation is different for different medium. So there is a one coefficient, attenuation coefficient. Since it is traveling linear, straight line in a medium, linear attenuation coefficient. You remember, it is your friend. Linear attenuation coefficient mu. It is mu. It is different for different material. Okay. So this mu is due to three interactions. One is due to photoelectric effect, second one for Compton effect, third one is pair productions. So it is function of these three. Mu is equal to mu Pe plus mu C plus mu Pp. Mu Pe मतलब photoelectric effect, C मतलब Compton effect, Pp मतलब pair productions. So it ultimately depends on these three interactions to calculate how much intensity of gamma ray absorbed in the medium. For that, we will derive a small simple equations. That equation represents what intensity entered into the medium. Suppose from here to here medium is there. So it has traveled a thickness of dx. So here it is entering, it is traveling here and it is coming out. Suppose it is moving along x-axis. So when it is entering, I am calling the intensity is I0 or I0. When it is coming out, it is Ix I am calling. This I0 is greater than Ix because in the between these 2 points, the medium is there, no? Medium absorbed the gamma rays. So how the intensity, where is a different point you can call. Suppose this is a medium. Here what is the intensity? I0. Here some distance x, Ix I am calling. At Ix distance, what is the intensity of gamma ray? Simple equations we will derive. Now we will derive how intensity of gamma ray changing when it is passing through the medium. Okay, I told you the initial intensity when it is entering into the medium. You take this is a medium. Here it is entering gamma ray. The initial intensity I0, it entered. It is traveling a distance. This is thickness. Let me call some x thickness is there. So when it is coming out, here the intensity I am calling Ix. At some point, it may be anywhere. If the medium may be persisting, it may be some more thickness also there. At any point you can say. At some x distance, still it is medium may be there here also. So at x distance within the medium, it may be outside the medium also. Okay. So here the amount of energy absorbed or amount of intensity absorbed in the medium, so that is di I am calling di. This is proportional to initial intensity. It is proportional to initial intensity and how much distance it has traveled. Suppose it has traveled a distance. Okay, this is dx I am calling. This point I am calling at x. Okay, thickness is dx. So this amount of gamma ray absorbed in the medium is proportional to intensity and how much distance, linear distance it is traveled. I am assuming this is x-axis. That's why I am writing x. Okay. Now proportionally constant you have to keep. No, for a particular medium there is one proportionally constant that I can write di is equal to mu into I into dx. Here I am putting minus. Why minus? Because this di is absorbed in the medium. The final intensity minus initial intensity. The final intensity is smaller than initial intensity. So di will be negative. That's why minus I am writing. So you bring this side here. Di by I is equal to minus mu dx. You do simple integration like this. Integration of di by initial intensity I am calling I0. After traveling a distance Ix. So here initially traveling entering is 0. It is traveled a distance x, let it be x distance it is traveled, that is somewhere here. Okay. So di by I is ln I, natural logarithm I. You put the limits I0 to I equal to integration of dx, x, mu is constant, you take out, so minus mu into integration of dx is x, so limits you put from 0 to x. What you will get, I am writing here only. So here I upper limit ln I minus ln I0 equal to mu into x is equal to 0 you put. So here minus is 0, minus you put in the bracket x minus 0. So ln I minus ln I0, what you will write? Ln I by I0 is equal to minus mu x. This base is E is the base. So I by I0 is equal to e power minus mu into x. So I is equal to, this I means Ix, no? You put here, this is Ix at x distance. Okay. So Ix, this is also Ix is equal to I0 into e power minus mu into x. So the intensity of gamma ray as it is passing through the medium decreases exponentially. Exponentially it will decrease. So Ix is equal to I0 into e power minus mu x. This mu is function of photoelectric effect, Compton effect and pair production. That also we'll discuss. You see that exponentially intensity is decreasing. So this mu is function of three effects. One is photoelectric effect plus Compton scattering, mu c, and pair production, mu p and p. So this interaction takes place differently for different atomic number, means different materials. Now we will do some graphs. If you take logarithm of this, what you will get? Log of Ix. Log means natural log only. Log of Ix is equal to log of I0. Here logarithm of E means you will get base will be 1, no, ln E to the base E1. So you will get minus mu x. If you plot the graph for a particular medium, so this is thickness of the medium. This is intensity, logarithmic intensity. How ln Ix changes? When x is equal to 0, if this is 0, ln I0 will be there. So somewhere here you take. So this I am calling, this point I am calling ln I0. So this point means when it is entering ln I0. Okay. Now the graph looks like this. Graph looks like this. So it is a straight line with a negative slope. What is the slope? Slope is mu. From the graph you can find out what is the mu. What is the mu? Mu is linear attenuation coefficient. Attenuation coefficient. So this mu also we refer sometimes as absorption coefficient. Okay. So here, since I am using the gamma ray and material when it is passing through a medium, attenuation I am using. So mu is linear attenuation coefficient. So this mu is depending on photoelectric effect, Compton effect and pair production. So this happens differently for different media. Okay. Now we will discuss some case study. It is like a case study. Two different materials will take. One is aluminium, another one is lead. For these two materials, how this linear attenuation coefficient is changed with energy of gamma ray. The higher the energy, lower the probability of photoelectric effect and Compton scattering. But for pair production, higher the energy, higher the pair production. Energy should and must be more than 1.02 mega electron volt. Okay, that we will discuss in detail. Aluminium and lead. What is the difference? You can find first. The atomic number for aluminium is less compared to atomic number of a lead. Atomic number is less means less number of electrons are there. Atomic number of lead, it is higher means higher number of electrons are there. When number of electrons are more in a particular atom, the gamma ray interacting with that atom, the gamma ray can dislocate electron from any energy level. The probability of knocking out of an electron may be ground state or excited, first excited state, second excited state, and so on. So, by understanding the atomic number, the dependency for the interactions, we can plot the graph for different coefficients, mu Pe for photoelectric effect, mu C Compton effect, mu Pp pair production. How these three are changing with energy of gamma ray for two different materials. One is for aluminium, one is for lead. That graph now we will plot, we will understand why it is so. Now see the graph. X-axis is energy of gamma ray, y-axis is linear attenuation coefficient. Linear attenuation coefficient, that is mu. The unit is meter inverse. It is function of all three. So x-axis starting energy of gamma ray. We differentiate X-rays and gamma rays by a boundary of 0.1 mega electron volt. We are approximately following this method. If energy is more than 0.1 MeV, I am calling that as a gamma ray. The most important is gamma ray coming from the nucleus. So based on statistics, the gamma ray energy mostly starts from the 0.1 mega electron volt. The X-rays energy also can be more than 0.1 MeV. But that X-ray we cannot call as a gamma ray because it is outside the nucleus. So I am taking the gamma ray energy from 0.1 mega electron volt up to 10 mega electron volt. You know the equations. Probability for photoelectric effect is proportional to Z to the power of n by E cube. And Compton effect proportional to Z by E. Pair production proportional to Z square into E minus 1.02. This K1, K2, K3 are just constants. Now we will see how the photoelectric effect graph changes. From here, if you take the graph like this, so it will end up here. The photoelectric effect for the lead, it is not exactly straight line, slight curve is there. This is for photoelectric effect Pe. I will tell this mu Pe. For lead Pb. For lead it is like this. Why? If energy is increasing, the photoelectric effect probability decreases. The photoelectric effect interaction decreases. That is why somewhere started here at 0.1 MeV. 0.1 MeV, the photoelectric effect, the attenuation coefficient is maximum. After that it is decreasing, it is almost 0 at 5 mega electron volt. For the lead, it is different for different material. Next, Compton effect. So here, energy of 0.1 MeV, only photoelectric effect takes place? Not sure. Compton effect also can take place. That is why Compton effect also you will find somewhere here. Okay, somewhere here, it will end here. It will end here. This is for mu C for lead. For lead. So here what you have to see carefully, when energy of gamma ray is 0.1 MeV, photoelectric effect also taking place with a high probability, that is here. Compton scattering also taking place with less probability compared to photoelectric effect. At 0.1 MeV, will there be any pair production? Impossible. Pair production minimum energy required is, that is 1.02 mega electron volt. So you cannot think of at 0.1 MeV that will take place. Now we have to think, because these two graphs I have drawn. Now pair production you have to draw. Then how it looks? For lead, somewhere it is like this. It happens like this. You see graph like this. So the energy here, it must be 1.02. 1.02. As energy is increasing, pair production is increasing. This is for mu pp, pair production for lead. For lead. You're understanding now what is the beauty of this? So minimum energy required is 1.02. Above 1.02 you are getting these probabilities. Now we have to go for ultimate mu. Mu is linear attenuation coefficient. That includes P, PB and PP. So all together you have to add, no? Add this plus this, and here pair production is not there. So here this plus this you are adding. It is approximately, if you are adding this, it should be more than this, no? Somewhere here. This is logarithmic scale. So 10 power 2 plus 10 power 4, just like 10,000 plus 1,000, 11,000. Jada difference nahi hota hai. So it is almost very near to this line. After that what happens? Up to here, it is increasing. Up to here, this is combined effect I am writing. It is adding, no? Up to here, here, it is coming down. So because it is after, from here, this is adding, this is addition or add. Then what happens? It will slowly turn. So this is the effective linear attenuation coefficient for lead. Because I am adding this one, photoelectric effect, plus this is Compton effect, plus here pair production is there. So up to here, you are adding only two. That is photoelectric effect plus Compton scattering. After this, it is turning. What is the beauty of lead? I am telling especially lead. After some energy level, the mu linear attenuation coefficient is increasing. So this is coming to lowest energy 4 mega electron volt. After 4 mega electron volt, the linear attenuation coefficient is increasing. So lead is the best shielding material for the gamma rays. Even though high energy gamma ray is coming, it can absorb, it can attenuate. That is the beauty of lead. Why in most of the nuclear reactors they use this lead as a material for the shielding of gamma ray. The most hazardous is gamma ray because it can travel more distance. Even though specific ionization is less, but it will travel a long distance. So we have to choose a material like lead, because the linear attenuation coefficient is increasing with energy also. After 4 mega electron volt, it is further increasing. So approximately maximum energy around 10 mega electron volt of gamma ray you can take. The 10 mega electron volt gamma ray also you can attenuate by choosing a appropriate thick material of a lead. Okay, now we will go for aluminium. Comparison sake, aluminium, how it affects. You know, the atomic number is less compared to lead. So what you will think? The photoelectric effect, I am sure it cannot be like for a lead. Then how it looks? It looks very simple. Somewhere here it starts. Somewhere here it starts. It will end here. This is photoelectric effect for aluminium. For aluminium, the probability is very less. The photoelectric effect is very less for the aluminium compared to lead. The main reason is the binding energy of electron in the aluminium is less compared to binding energy of electron in the lead. Hydrogen atom ground state energy minus 13.6 electron volt. Hydrogen like atoms energy, the formula is minus 13.6 into Z square divided by N square. N is the principal quantum number, Z is the atomic number. So higher the atomic number, higher the binding energy. So for the lead, Z is much higher, so binding energy will be higher. So higher the binding energy, the photoelectric effect means it will absorb the energy from the gamma ray, the electron will be free from it, and electron moves with some kinetic energy. So compared to the binding energy and 0.1 MeV, 0.1 MeV energy is very high for the aluminium atoms electron binding energy. If binding energy is very small compared to the energy of the gamma ray, it will jump into the Compton effect. With the Compton effect, what happens? You will not realize that electron is coming out from the atom because the binding energy is so low compared to the gamma energy. I am comparing, be careful. Compared to the gamma energy, the binding energy is very small. So that's why Compton effect dominant. The Compton effect also, electron is taking the energy from the gamma ray. But that is negligible. You have 1 lakh rupees, you have given 10 rupees. How does it matter? Nothing. So with 10 rupees, electron is coming out. So that's why the Compton scattering dominates in the aluminium. How it looks, I will tell you. So this is the Compton scattering. Starts from somewhere here. Here it will start. Compton scattering. It will go like this somewhere here. So these two are, I am comparing. This is mu Compton for aluminium. Mu Compton for aluminium. So that's why it is more than compared with photoelectric effect. The Compton effect is more in aluminium. But in lead, it is ulta. Lead photoelectric effect is dominant when energy is 0.1. Because 0.1 energy is less compared to the binding energy of the electron in the lead. That is why this graph is like this. And that is why this graph is like this. Then what effect? Pair protection. Pair protection, definitely you need minimum energy. That is 1.02. Then how it looks? Will it take place at 1.02? 1.02 it will not take. It is taking some more energy. Somewhere here. Somewhere here it is taking. somewhere here it is taking, this is for pair production for aluminum. For the lead, the pair production started from just after 1.02, but for aluminum it is taking minimum around near to 4 mega electron volt. Why? For pair production, aluminum is taking more energy gamma ray to produce a pair production. I told you the pair production takes place when gamma ray go to the nucleus very close. The nucleus very close. You are close to the nucleus means the nucleus contains protons and electrons, protons and neutrons. Nucleus contains protons and neutrons. Neutral in charge, proton is positively charged. Positively charged means it is giving a electric field. So the gamma ray photon has to see the high electric field. You see aluminum and lead. The lead atomic number is more, number of protons are more electric field it will see. When this gamma ray photon sees more electric field, it will become pair production, electron and positron. That is why here when you see the pair production taking place in aluminum, significantly higher energy, because the aluminum nucleus giving the electric field is less compared to lead. So this is the beauty of this graph. Huge physics is involved in this. I hope you understood. You just watch this video and each and every sentence what I am telling, observe it. Okay, my dear brilliant subscribers, thanks for watching this video. At the same time, you share this knowledge to your friends or relatives. Okay, by sharing knowledge you will gain the knowledge. No loss for you. Thanks for watching. Please subscribe my channel if you didn't. Thank you.